September, and his book was written by Thierry Poinot, Jean-Claude Trigeassou, and myself. And this book provides all developments about partial moment tools, mathematical tools used for the parametric estimation. And this book retraces all development for more than 40 years in the LIAS Laboratoire, le Laboratoire d'informatique et d'automatique pour les systèmes, at Poitiers, at the University of Poitiers. My talk is divided in three parts. In the first part, I show you the principle of the partial moment. And in the second time, I show you the different chapters in this paper. And I make a focus on one chapter about the similarities between partial moment approach and algebraic framework identification approach. Well, the principle, let's consider a simple case, first order given by this ordinary differential equation, and we want to estimate in the context of the continuous time, direct continuous time identification, we want to estimate A0 and B0 by using linear least square methods. We have the data with U and Y, the input and the output. And in this context of the direct continuous time identification method, we have different ways to do this. We can use an output error procedure, for example, by using an iterative procedure. But we want to obtain an estimate in a single step by using linear least square, as mentioned before. And in this context, we call this kind of method equation error method, and there are three different categories of methods. The method based on filtering, on integration, or based on modulating function. And I'll show you that the partial moment based approach can be classified on these two classes, methods based on filtering or an integration. Well, to obtain a linear least square, we have a problem with this ODE in continuous time because we have here the derivative of the output, which is in general unknown or unmeasurable. To deal with this problem, we apply a multiplication of the ODE by t, and we apply an integral on the interval 0, capital T. In fact, we apply a partial moment. Here you have the definition of the nth order partial moment, and we apply, in fact, a first order partial moment to the ODE to remove the derivative of the output. And we can rewrite this equation as follows here. And Y0 is a real output at the instant t. And we can compute from measurement of this real output, a noisy output measure, of course, we can have an approximation of this output at the instant t here. I substitute here y0 by y, the noisy output. And we can prove that this formulation presents a minimal variance for an optimal interval T out. And we have an approximation, a nice approximation of the output, real output at the instant T, and we would like to use every data to make the estimation, and we introduce for this a new definition of moment called reinitialized partial moment by this equation. And we substitute in the previous equation partial moment by the reinitialized partial moment defined here. And you can see with this formulation, we have an integral on an interval 0 t at, and we have a sliding windows. We allow us to consider every data set. And this design parameter T at here is selected close to the optimal T out previously defined. Okay?
Is there a difference between T and T hat?
Here, the T here and T hat. Here, we can, the T can be modified between 0 and the horizon of the dataset. And here, you select one width of the partial of the integral, and it's fixed at the beginning of the study to estimate data. You see? Mm-hmm. Okay. And we can reformulate this equation 4 in a regression form by separating parameters and data. And we can apply a linear least square to estimate A0 and B0. Okay? With this definition, we can see a definition which is close to the convolution product, and we can reformulate this equation 4 in this form by using filter formulation. And it's the same equation as before with the convolution product between filter and the output here, the input here. And we can reformulate this equation 4 with this convolution with a filter, which is a finite impulse response filter defined by this equation. And if we select T at close to the optimal interval, as mentioned before, we have this minimal variance representation. Then, with this very simple example, I prove that our methods can be classified in integration-based methods because we compute integral with moment, and with this formulation, we prove that the method is also in the class of methods based on filtering. We use linearly square with, in the regressor, our noisy data. Of course, the estimate is biased, but we can use this first estimate with an instrumental variable method or natural error methods to remove the bias. To summarize this first part of my talk, we have a methodology which we can apply to a linear time invariant system. We have a matrix formalism in the book for any order, system order NA. And we can here mention the fear filter, the implicit fear filter in the general case with system order NA, and the reinitialization interval T hat allow us to adapt this design parameter to the type of noise. We can use tuning parameters which is adapt to a white or a coloring noise. And all development I show you in the continuous time, we can realize the same development in discrete time context. And we prove in the book that the implicit fear filter in discrete time is close to the ideal filter of Stiglitz-Maillard. The content of the book, the application to linear time invariant system in continuous time and discrete time are described in chapter 3 and 4. And in chapter 5, we see the analogy between this approach, partial moment approach, and the algebraic approach. And I'll make a zoom after on this chapter. And we use the implicit field filter to develop a continuous time subspace-based methods in the chapter 6, and continuous time linear parameter varying model in chapter 4. And recently, we apply these methods to estimate the parameters of a partial differential equation. And to do this, we introduce the definition of the multidimensional partial moment. And I show you in May 2022 here in the city identification, an application to a bird population. Do you remember? I use this multidimensional partial moment at this occasion. Okay, I would like to present the analogy, the similarities between these two approaches. I would like to show you the principle of the algebraic framework of for linear identification introduced by Michel Fliss and Hebert Sierra Ramirez 20 years ago. And the principle of this algebraic method, I show you this principle with this example. Let's consider a second order system with this ODE with 1, 0, and we want to estimate these four parameters, A0, A1, B0, B1. And the principle of the algebraic approach in first step, we realize, in the Laplace domain, if the initial conditions are non-null, the ODE in the Laplace domain, we have this equation with y, the initial condition on the output, y0 on u0 here. Donc, then the principle of the algebraic approach in the first step is to make derivation with respect to S to remove this part of this equation, to remove all initial condition contribution. For this example, we have a second order system. We make a derivative of the equation 6 2 times with respect to S. And in a second step, we build a system of linear equations by multiplying this derivation successively by S power minus I with I greater than the system order. In our example, greater than 2. And we build a system with 4 equations because we have 4 parameters to be identified, estimated. And in a third step, we solve this system of linear equation by using data S power minus 3, it's a triple integral. S power minus 4 is a quadruple, and so on. And the last step, the last but not the least, we must choose the instant where I select the estimate. Okay? It's not an asymptotic method. It's just a method with a system of 4 linear equations that we solve, and we must select the instant or the instant where I take the estimate. And this last step is very sensitive. In the literature, we can find different criterion to select this, and we propose in the book an efficient criterion to select this instant. The analogy between both methods, algebraic approach and the partial moment approach, here the multiplication by S power minus G is a repeated integral. The derivative with the I derivative is correspond to this multiplication by the variable tau, which is the time power I. And if we use the Cauchy formula of the GIF repeated integral, we have a single integral with this multiplicative term here. And to conclude, the algebraic approach can be reformulated with a partial moment defined by this equation. And we prove in the book that we have exactly the same solution between both approaches by using the Fliss procedure or the partial moment approach. And from this equivalence, we propose a new implementation of the algebraic framework by using the fundamental equation introduced by Jean-Claude Trigeassou during his PhD thesis in 1987. Here you have a matrix formulation, and each line of this matrix definition, it's a linear equation. We have a system of linear equations, And this system link the parameter B, the parameter A, and the partial moment of the input on the input on the output. And we have also the initial condition here with the state vector x0, and to remove this unknown initial condition, we skip the first two lines in our example with a second order. The size of the state vector is 2, and we skip these two first line, and we arrive to the same system. We arrive to a system of linear equations, and we prove that the same development as the Bliss approach. If I come back to our example, we must take in this fundamental equation the third line to the eighth line. We have 4 parameters, and we have this vector, the state vector at the instant t, to consider also. And we have this matrix equation like this, by taking this line from the third to the eighth. And to remove the term with xt, which is unknown, we use an orthogonal matrix. We use this notation, x orthogonal transpose time x equals 0, to obtain this matrix equation, and we must inverse this matrix here to obtain an estimate of the parameter vector theta t. To summarize, the Bliss method is this one. We have a system of 4 linear equations. We can rewrite this system on by using this formulation, this matrix formulation. By using the fundamental equation developed with the partial moment approach, we have this system of linear equation. And in the book, we prove that these two approaches yield to the same solution. In fact, these two systems is identical up to an invertible matrix, transformation matrix T, as mentioned in this theorem present in a book. And we must select the instant t where I select the parameter, and we propose this criterion. We have this matrix to be inverted, and we use the minimal value of the condition number of this matrix to select the instant where I take the parameters. Well, to summarize, our methods I present you in first part the application to a LTI system, but it's not for this application that the approach is interesting. It's interesting for a more complicated problem like a continuous time LPV model. And when we have no information about the parameters, it is interesting to use this kind of methods to obtain a first estimate and to initialize an instrumental variable methods, for example, algorithm. And we apply this approach for PD model estimation, nonlinear system estimation, and we have one perspective to use an algebraic approach applied to a fractional order system, but it's not done actually. And keep in mind that the approach is used in the first step and to initialize an iterative procedure, for example, to obtain ReOp, for example, when we optimize, minimize a criterion to optimize to obtain the global minimum. That's all. Thank you for your attention.
Thank you, Regis. So we have some time for questions. Well, nobody. I have two questions. In your presentation, you didn't speak about noise. So when you do this integral, how is the noise treated? Does it disappear? Does it cause problems? And a second, can you tell us a little bit, because there are different ways to do continuous time identifications. And so why, in which case I have to use your method more than the classical ways to do, or just discretization. You could discretize the equation. You could use the method that's been developed in RC. So in which case do you have partial moments interesting? And so how is the noise treated?
As mentioned, it's interesting for difficult problems and continuous time LPV model, for instance. In the last SID symposium at Boston, we present an application to a wastewater treatment with the problem to we have a process, a nonlinear process,
yeah.
And we can easily represent this process, but the operating point move during the operating of the process, and we use LPV model to represent this, and we have used data given by le syndicat des eaux de Paris, compagnie of wastewater in Paris, in a global approach for LPV, and we have no information about the parameters, and we use this approach. We present this in the paper presented at CID symposium. To initialize an output error algorithm, a Levenberg-Marquardt algorithm, and we obtain a good result. It's an example.
Yeah.
Last May 2022, I present the PD estimate. And for to represent birds population dynamics.
But here you give examples, but yes. What is really technically or fundamentally the advantage of this method with respect to just the discretization of the derivative?
For all application present, we are in continuous time.
Yeah, I'm sure.
Yes, and
but you can discretize your model. So
no, the model is
continuous.
Is continuous.
In the computer, it will be discretized. So, indeed.
And
but you can still discretize it.
We use complete data to estimate parameters of the continuous
Yeah,
time
I know, but you can discretize your continuous time
Yes.
model in the discrete time model with an approximation. So,
Yes.
so why this is so? Because you don't make an approximation, or why is this better? It's sort of than just discretization of if you dy dt, it's yt plus 1 minus yt divided by t. You can
we can
invent.
is it better than this kind of discrete?
Yeah.
Do you remember the work of Hugues Garnier about the conceit toolbox? Do you remember?
No, but I work with
developed,
I work with my
yes,
PhD
and,
student.
when Nancy or Poitiers, we work on this direct continuous time identification method. We would like to use this context because we think that this is better to the methods which consist to discretize the model and to use after the transformation of the discrete model to the continuous one.
Yeah.
I don't remember exactly the better property of our method.
Any other question?
The similar question, are there cases where the method don't work? For instance, for a linear system distribution, so can I use this kind of method?
For the non-linear system?
Since this morning, the man has a linear system, so can I use this kind of method?
We can use for
because for me it's like a linear filter that you apply to your system on both sides. So
if we are here a nonlinear equation here, we apply the same manner this computation, and we arrive to reformulate this equation in a regression form and to estimate parameters. For instance, the presentation of the PDE model application 2 years ago, we have U square here somewhere, and we can make all development in the same manner than the LTE development here, LTE system development. In the book, there are an example with this kind of non-linearities with a square term here, and we can do the same computation.
it could be non-linear, but it should be linear with respect to the parameter.
Yes. Yes.
And also, so it's a linear. It's an integral filter, but you don't need to know the initial condition because you have a window.
No, just the question with initial condition, it's only for the algebraic approach.
Yeah, but when for example, when I want to implement a linear integration, so I need to recess the initial condition. So how do you do that for the initial condition?
There are no problem with initial condition when we have this regression here. We have data y, data on u, and we have no problem with initial condition. We have just implement this integral here. It's not, there are a confusion with the presentation of the algebraic identification. Here we have a problem with initial condition in algebraic framework with the initial condition of u and y, but it's not the same methodology with this equation with reinitialized partial moment. Okay.
Not necessary because we have an ODE to solve, to have a numerical integration method, and I have to know what are the initial conditions to solve my equation.
I'm not sure to.
Quand une équation différentielle à résoudre, j'ai besoin de méthode.
Ah, mais je résous pas l'équation là. Hein. Non, j'ai des intégrales dans chacun de ces termes, et j'implémente ces intégrales avec mes données mesurées.
On intègre
de 0. Ouais.
L'application, on connaît la valeur de la fonction.
C'est ma mesure. It's my, it's the first sample of my data set. No, there is no problem with it. In the regression form here, we can compute this moment of the one from all data set on Y on U.
Because it's a simple problem, but when you have a lot of state variables, you don't know all the necessary
in the
value of the states.
In the linear time invariant system, there are no problems with the initial condition.
Okay, we'll let that for the discussion afterwards. So we'll thank Regis once again for his presentation.